Representation theory for enhanced machine learning, mathematical foundations, and applications. Hello everyone, thank you for joining me today. My name is Sakar Kiv, and I'm excited to discuss how representation theory can be applied to machine learning and the benefits of making these models more explainable. This presentation will cover the basics of representation theory, its applications in machine learning, and several real-world examples in different domains. Representation theory is a branch of mathematics that studies how algebraic structures such as groups act on vector spaces. It helps us understand the symmetries in mathematical objects and has broad applications in physics, chemistry, and computer science. In the context of machine learning, representation theory provides a framework for understanding how transformations and symmetries can be applied to the data. So just like we can see, representation theory can show how we can translate the rotation of this hexagon. We can represent flips. If you were to see this hexagon flip, that could be a representation, or even a diagonal flip. And we can even translate by flipping the other half on the XY axis. Explainable machine learning is crucial because it allows us to understand, trust, and effectively use our models. By making our models more transparent, we can ensure that they are fair, identify biases, and improve their performance. Representation theory can help in making ML models more explainable by providing a mathematical foundation for understanding their behavior. So here we have some tenets of explainable AI. We have transparency, fairness, trust, robustness, and privacy, and interpretability. Representation theory can help with this. Group theory, a key component of representation theory, deals with the algebraic structures known as groups. Groups are sets equipped with an operation that combines any two elements to form a third element while satisfying four conditions. We have closure, a group G, and that is a multiplication sign, is a set G closed under a binary operation for multiplication such that the following axioms are satisfied. And we have the conditions of associativity of this multiplication operation. For all A, B, C as a member of G, we have that parentheses A times B times C equals A times parentheses B times C. And we even have the identity property element for E for multiplication. There is an element E in G such that for all X as a member of G, E times X equals X times E equals X. And we have the inverse or invertibility of A apostrophe of A. For each A as a member of G, there is an element A apostrophe in G such that A times A apostrophe equals A apostrophe equals A equals E. In machine learning, we often encounter groups when dealing with transformations such as rotations, translations, and scaling. By applying group theory to machine learning, models can better understand how data transformations affect our models. For example, in a neural network, we might want to ensure that the network's output is invariant. So we have different examples here. We have translation invariance, we have rotation invariance on this traffic sign, and we have scale invariance. So the network's output is invariant to certain transformations, as seen here, of the data input. Group theory helps us design networks that respect these symmetries, leading to more robust and explainable models. Here's where the math comes in. We use group actions to handle symmetries in data. For instance, consider scaling transformations in our feature space. We represent these transformations with matrices. For example, let us use this scaling matrix T. We have alpha and beta as our scales. When applied to a feature vector X, it scales the features proportionally. And our features here, in this case, is credit utilization, payment history. This ensures that similar profiles are treated consistently, even if individual features changes. An example that we can get into is loan default prediction. Consider predicting loan defaults. Suppose we have features like credit utilization and payment history. Using a scaling transformation, we can normalize these features to ensure consistent treatment across different profiles. This helps us in making fair and robust predictions, as similar profiles will have similar predictions regardless of the scale of individual features. So to see how this works, let's apply the scaling matrix to a feature vector. Suppose we have a feature vector X representing a credit profile. In that vector X, we have features credit utilization and payment history. When we apply the scaling matrix T, shown here by alpha and beta, to X, our vector shown up here, we get this operation. We have a scale of alpha times credit utilization versus beta times payment history. Here we can see how group representation is very useful, and concepts of groups are applied here. In insurance, assessing risk accurately is critical. By applying group theory, we can understand how different risk factors interact. For example, using a rotation matrix, we can analyze the relationship between age and annual income experienced to assess car insurance risk. This allows us to capture complex relationships and make more informed decisions. So if we were to apply a rotation for a feature vector X, we have age and annual income, and we have a theta, which is 45 degrees. We take that theta, we multiply it by our vector X, and it gives us this new transformation. So age and annual income might be correlated, and rotating the feature space helps uncover hidden relationships. The application would be rotation may reveal a new dimension where the combination of age and income shows stronger patterns related to insurance risk, improving prediction accuracy. So here we can see a combination of age and income as a new matrix representation. In commercial real estate, investment decisions depend on various factors like property value, location, and market trends. Using translation transformations, we can align data from different properties to a common scale, making it easier to compare and analyze investments opportunities. This helps us in identifying the best investment options with greater accuracy. So here we can see that the translation matrix T, we can adjust the feature values where dx and dy are translation amounts. When we apply this translation, we have x, our feature vector with rents, price, operating costs, and we have our translation amounts here. And we can see in this scenario, adjusting rent prices and operating costs to align with regional benchmarks can normalize data for better comparison. An application would be translating rent prices and costs helps to compare properties more fairly against market norms involving investment analysis. Let's apply these concepts to animal operations. Imagine we have two shelters with using different capacities. Using a scaling matrix, we can allocate resources like food and medication proportionally to each shelter's capacity. This ensures that both shelters receive adequate supplies based on their size, improving efficiency and animal care. So we can see with the scaling matrix is standard resource allocation per animal is food per animal, and we have a medication per animal. You can use a scaling matrix to adjust these resources based on their shelter size. We can see that shelter A needs 50 units of food and 50 units of medication, and shelter B needs 100 units of food and 100 units of medication. This scaling ensures that shelter B, being larger, receives twice the amount of resources compared to shelter A, reflecting their larger capacity. So giving these scaling matrix, we can easily see that shelter B needs twice the amount than shelter A. This is how group theory and representation theory come together to help us represent and be able to explain in detail what these numbers mean to show stakeholders how with this matrix operation, or how we can show and explain what is actually going on with capacity in this case. Another application is identifying trends in intake and adoption rates. By rotating data matrices, we can uncover patterns. For example, rotating the matrix a monthly intake and adoption rates might reveal that increased intake rates lead to delayed adoptions. This insight can drive strategies to improve adoption rates. So in the scenario, you observe relationship between intake rates and adoption rates. And here we have the data, monthly intake and adoption rates for 6 months are recorded. And we have a rotation matrix. If we rotate this data matrix, we can analyze trends. We can apply the rotation to the data to see if there are trends between intake and adoption rate changes. Rotating the data matrix may reveal patterns such as increased intake rates lead to delayed adoption rates, prompting actions to address this trend. So aligning actual costs with budgets is crucial. Suppose the shelter's monthly budget for veterinary care is $3,000, but actual costs are $3,500. By translating the actual cost data to fit within the budgetary matrix, we identify a $500 overspend. This helps and revising the budget or finding cost-saving measures to ensure future costs align with the budget. High rejecting rates can negatively impact adoption rates. Reflecting the data matrix of rejection and adoption rates can show if higher rejection rates correlate with lower adoptions. This insight helps to us reduce rejections and improve adoption rates, enhancing overall shelter operations. In summary, representation theory and group theory provides a powerful tool for machine learning models, more explainable by applying transformations like scaling, translation, and reflection. We can better understand and manage data in various domains, from loan default predictions and insurance risk assessments to real estate investments and animal shelter operations. Thank you for your attention. I'm now happy to take any questions. Thank you.